When we are looking at waves on a string, because we have to have nodes at the two ends of the string where it's fixed at the pulley and at the vibration generator, what we find is that only certain frequencies and wavelengths, certain wavelengths will actually fit the string. And these correspond to what we can call resonant frequencies. So here the first stationary wave pattern we can produce is when we have one loop on the string. And so the length of the string here between the vibration generator and the pulley corresponds to half a wavelength. So one wavelength is twice the length of the string. And here, if you look closely at the vibration generator here, that corresponds to a frequency, in this case, of about 17 Hertz on this particular string. If we increase the frequency above 17 Hertz, as we see here, what we will do is we'll really lose the standing wave pattern completely, and we'll get very little displacements along the string. But as we increase the frequency further, reducing the wavelength, we'll eventually get to the point where we can fit two loops on the string. So now you see here at 34 Hertz, the length of the string here is equivalent to one wavelength. So the distance between the two nodes is half a wavelength. We've got two loops on the string, so the full length of the string here is one wavelength. If we reduce the frequency further again above 34 Hertz, again we will lose that standing wave pattern as we go above that resonant frequency, and really we see very little displacement along the length of the string. But as we increase the frequency further, again we will reduce the wavelength until eventually we get to about 51 Hertz, and at that point the length of our string corresponds to 1.5 wavelengths. So we can fit 3 loops on the string. We have our third resonant frequency. So we can see that there with nodes at either end of the string, and also 2 further nodes at positions along the string. So we've got 3 loops on the string. Now if I increase the frequency again beyond that, again we lose that pattern, but as we get further along here now, so get to about 68 Hertz, okay, which is 4 times that, what might call that fundamental frequency where we had one loop on the string. What we've now got, if you look very, very closely, you can just see 4 loops on the string, because now the length of our string corresponds to 2 wavelengths of this wave. Now in the case of the first standing wave pattern, stationary wave pattern that we saw there, what we found is that it occurred at a frequency of 17 Hertz. Now that is what we call the fundamental or first harmonic frequency. And we saw that that occurred at 17 Hertz in our example. Now the wavelength of the standing wave pattern then that was produced there, well, don't forget, always in a standing wave pattern, the distance between 2 successive nodes is always half a wavelength. So half a wavelength would have been 2.4 meters. That was the length of my string, was 2.4 centimeters in that example. And so the wavelength here would have been 4.8 meters at that particular frequency, and that is sufficient then to produce this stationary wave pattern with one loop on the string. Now as I go above 17 Hertz, then that stationary wave pattern will disappear. Okay, as I move away from that resonant frequency, we won't really see anything much at all on our string. The amplitude will be negligible really at all points along the string. But as we increase the frequency further, eventually we saw that we formed 2 loops on the string. Now what we have there is the second harmonic frequency, which we found occurred at 34 Hertz. Now remember, wave speed, waves, the speed of the waves is frequency times wavelength. But the speed at which waves travel down a string depends really only on the tension in the string, which we haven't changed. And so because the speed with which the waves would travel down the string is constant, when I double the frequency here, from this first harmonic frequency to the second harmonic frequency, we've doubled the frequency. Doubling the frequency will halve the wavelength. And so what we're finding now basically is we're getting 2 loops on the string, because the wavelength now just corresponds to the length of the string. Okay, so the half a wavelength there is half the length of the string, which is 1.2. Double that, 2.4 meters. Again, as I increase the frequency above 34 hertz, away from that resonant frequency, the pattern will disappear. But if we keep increasing the frequency further, eventually we get to a third harmonic frequency. That occurs at 51 hertz. Half a wavelength, then the distance between two successive nodes is 1/3 of the length of our string, which is 0.8 meters. So the wavelength here is now 1.6 meters. So comparing the first harmonic to the third harmonic we have 3 times the frequency, and therefore just 1/3 of the original wavelength. So we can fit 3 times as many loops on our string at resonance. Resonance occurs again at 68 hertz, where we find our 4th harmonic frequency. This time the distance between two successive nodes is 1/4 of the length of the string. The length of the string was 2.4 meters, so half a wavelength, the distance between two successive nodes, 0.6 meters. So the wavelength here of the waves could be found by doing 2 times 0.6 meters is 1.2 meters. So notice here that the harmonic frequencies here are occurring at multiples of the first harmonic frequency, what we sometimes call the fundamental frequency of the stationary wave pattern. So here, if the fundamental is at 17 hertz, the second harmonic is at 34 hertz, the third is at 51 hertz, the fourth is at 68 hertz. We would have found a 5th harmonic at 85 hertz, and so on like that. Every 17 hertz you'll get another loop on the string. Now, we have said already that the speed of waves travelling down the string will be equal to the frequency of the waves multiplied by their wavelength. For the experiment that we have just demonstrated, the speed of the waves was kept constant. However, the speed of the waves will be dependent on the tension of the string. If we change the tension of the string, we can change the speed with which waves will travel down our string. And that will change the frequencies at which we get resonance. That is, the frequencies at which these standing wave patterns appear. Just rearranging that formula above there, we can say that frequency of the wave will be speed divided by wavelength. Now, if you imagine the fundamental frequency, or the first harmonic frequency here, that was 17 hertz in the example that we showed above, if we increase the tension in the string, that would cause the waves to travel more quickly down that string. The incident wave that travels down from the vibration generator to the pulley would travel more quickly. The reflected wave would travel back more quickly in the opposite direction. But to produce this first harmonic frequency, the wavelength of the waves will still need to be 4.8 meters, because the distance here from the nodes at either end of the string will need to be half a wavelength. Now we know that distance there, our string was 2.4 meters long, so half a wavelength will still have to correspond to 2.4 meters in order to produce this first harmonic frequency. Therefore, if the wavelength at which these harmonic frequencies appear is still the same, but the speed has increased of the waves on the string, that means the frequency that we need to set the signal generator to, and the vibration generator, and get that moving at that frequency, the frequency that we need to get that vibration generator moving at will be greater than it was before. It can be shown that the frequency of the first harmonic depends on the tension in the string, the length of the string, and the mass per unit length of the string. So here in this formula, F is the frequency of the first harmonic, T is the tension in the string in newtons, L is the length of the string in meters, and mu is the mass per unit length of the string in kilograms per meter. Okay, so we have an example problem here, very similar to the situation that we saw earlier in the experiment that we demonstrated. One end of a string is tied to a vibration generator, and the other end is extended over a pulley and used to support a 300 gram mass. If the length of the string between the vibration generator and the pulley is 2.2 meters and its mass per unit length is 0.42 grams per meter. Find the fourth harmonic frequency. Okay, well, no problem. We're going to start with the formula then. So that formula is in your data book. You don't need to recall it, but you do obviously need to know what the terms mean. T is the tension in the string, L is the length of the string, mu is its mass per unit length. F is the frequency, but it is the frequency of the first harmonic frequency. That is when one loop is produced on the string, not the fourth harmonic, which will produce 4 loops on the string. However, if we can get the first harmonic frequency, determining the fourth harmonic frequency from that is trivial. So let's put some numbers in and let's find the first harmonic frequency. So the length of our string is 2.2 meters. Tension in the string will be the mass that it's supporting, or the weight of the mass that it's supporting. And then we need to put in the mass per unit length. Now we need to work in SI units because we put the gravitational field strength here in newtons per kilogram. The newton is an SI unit. We need to work with the SI unit of mass here as well, which is going to be kilograms and not grams. So we need to convert this. Now, the way to do that then, 0.42 to change from grams to kilograms, we're going to divide by 1,000. So that will come, when we do that, that will become 4.2 times 10 to the minus 4 kilogram per meter. And let's work that out. So when we've calculated that, we have 19 hertz. Now we must remember that that is for the first harmonic. The other harmonics appear at multiples of the first harmonic. So the fourth one is simply going to be 4 times 19 hertz, 76 hertz for the fourth harmonic frequency.